Welcome back to ELE 112, Chapter 8, Section 3, which is called Source Conversions. The first few sections talk about voltage sources and current sources and how they have internal impedance. They're under the heading of circuit theorems and conversions. So, I don't know how well your book describes it, but I'm going to give you a little bit of a background. There's more than one way to solve a circuit. You can use current divider, voltage divider, Kirchhoff's voltage law, Ohm's law, and there are also multiple ways to attack a problem. What we're going to be doing in parts of Chapter 8 moving forward, specifically in 8-3 and 8-4, I think is where we're going. No, 8-3 and 8-5 specifically, is learning about higher circuit analysis techniques. So I invite you to take a look at the pictures before you out of Chapter 8. The heading on that circuit says, Conversion of a voltage source to an equivalent current source. So, the theory behind it is that a power supply, such as this one here, which has an internal resistance, can be matched with a equivalent current source over here and a resistor, but it must be in parallel. So in other words, if points A and B, which are here and here, and here, are considered the exact same points, when I connect a load resistor, if you'll look at the bottom figure 8-8, when I collect the load resistor to the circuit, each of these resistors receives exactly the same amount of current flow, regardless of whether it's a current source or a voltage source. Now you're saying, well, maybe I just have a voltage source. Fantastic. Well, maybe I just have a current source. Fantastic. What I'm going to tell you is you're going to learn how to really easily convert from a voltage source, which you can see on either of these diagrams on the left, to a current source on the right. Now, they don't look the same, and one of them has a power supply right here, and the other one has a current source. I've got that. But at the end of the day, once you learn how to do this process, you will realize what's in this black circle, well, it's actually blue now, is true, that those two load resistors experience exactly the same current if you were to analyze the circuit using Ohm's law, voltage divider, or current divider. Now, because of that, if two identical resistors have exactly the same current, let's take a 1K resistor and a 10 milliamp current. If both resistors have 10 milliamps running through them, their voltage is V equals IR. And that resistor's voltage can be determined. So now you're going, oh, this is cool, but why a voltage source and solve the circuit? But if that's not the case, if you're having trouble solving it, sometimes converting your front end, your power supply side, to a current source of equivalent stature can simplify your analysis of a harder circuit. Very hard to imagine right now because this is just a bunch of hot smoke that I'm blowing at you, but it's true. So what you're looking at in figure 8-7 on the left is what a power supply looks like. What you're looking at on the right is what a current source looks like. It's so many amps with a parallel resistor. We saw this in section 8.1 and 8.2. Now, why are we doing this? We're doing this because sometimes it's easier to start forward. It is also possible to take, as shown in figure 8-11, a current source and convert it to an equivalent voltage source. As you can see there, the resistor that's used for both circuits is exactly the same. That resistor and that resistor never, did I say never? Never change. Their location changes. In the parallel circuit here, in the current divider, it's in parallel with the current source, whereas in the voltage source version of the circuit, it's in series. That's about it. That's about the only difference. So here we go. We've got a blank board before us. We're going to learn how to do a power supply voltage source conversion from a voltage to a current source. Let me clear my board here and draw my circuit. Let's go to black. It'll be a little bit more efficient. There we go. Okay, black. Here we go. Wow, that's not very black. Okay, so here is my voltage source. I'm giving it 50 ohms. I'm calling it R sub S. Now, the battery will be 100 volts. We'll just call that V sub S. And we want to convert what's at pins 1 and 2. We want to convert that to an equivalent 1, 2, 3 current source with a resistor that has pins 1 and 2. Okay, so here's how this works. Step 1, move RS in parallel. That's here. So we've installed it. We've got a current source, and that current source picks up the following equation. Ohm's law. The current source is defined by the battery on the left, which is 100 volts, divided by the resistor that you moved. So what you've got up there is 100 volts. IS is 100 volts divided by the resistor, which is 50 ohms. You end up with 2 amps. Your new circuit with 2 amps located here, where the green circle is, with a resistor in parallel of 50 ohms, performs, according to pins 1 and 2, exactly the same as pins 1 and 2 sitting on the left with the voltage source. Isn't that special? That's all you have to do to make the conversion. Take the battery divided by the resistor, as shown here. Take the battery divided by the resistor, and you get your new current source. Drop it in the circuit, you are done. That's it. Now we're going to go the other way. We're going to pick another page here, and we're going to take, and we're going to draw the opposite circuit. We're going to draw a current source. Let me change my dot definition so I don't, okay. Let's go with black. Okay, here we go. We have a current source. It is fed with a parallel resistor. Pins 1 and 2. 1K, and it's known as R sub S. Its value is 10 milliamps, and we call it I sub S. Kind of messy. I wish I could be cleaner. And we're going to convert it down here. We're going to convert it down here to a battery and a resistor in series. Now, step 1, move the resistor. So it's a 1K resistor, so we move it and we place it here and we call it the same thing that we've been calling it, and that's the area in red that you see. I have moved it, and all we have to do is calculate the voltage. That's all we have to do. Now, to calculate voltage of the battery, it's ISRS. And guess what? We have both of those. We have the current, it's 10 milliamps, and we have the resistor, it's 1,000 ohms, and if you multiply those out, they cancel each other, and you end up with 10 volts. That's your new power supply. You have now effectively learned how to convert a voltage source to a current source and a current source to voltage source on the fly. Beautiful, beautiful. So I'm going to continue here by doing a sample problem, but I'm going to take a small pause right now and come back and add a picture to this page. Okay, so let's continue with our analysis. Here's what we're going to do. On the left, in the color blue here, is a current-driven circuit. That means that 2 milliamps is coming out of the supply and feeding a parallel branch of 1,000 ohm resistors. On the right is the equivalent but different looking circuit. We took the current source and created a source transformation that delivers 2 volts, but we had to move the resistor in series with the battery to make it work. And in both cases, we have hooked up a 1,000 ohm load resistor. What we're going to find out after the source conversion, which is actually done before you, what we're going to talk about is why. Why are we source converting? The reason we are is the circuit on the left, if you look at it, it's a current source with 2 parallel resistors. Now, you have to either know through luck that 2 milliamps, if you notice, they're both 1,000 ohms, both branches here in the red, they're both 1,000. You know what's going to happen to that 2 milliamps. It's going to equally split, right? But what if those numbers were not good numbers? The only thing you can do to solve that circuit is use current divider. Well, what if you hate current divider? What if you believe the problem is easier to work as a voltage supply, or vice versa in this case? If you look at the circuit on the top left, it's parallel. The one on the right is a simple series circuit. If you were given the circuit on the left, by converting it through source transformations, you now have an equivalent series circuit. Now, I'm not suggesting the circuit on the left and the right work exactly the same way. What I'm suggesting is that this resistor that's circled in the green is not working very well. This resistor circled in the blue, both load resistors. They're 1,000 ohms. What I'm suggesting is that if those two resistors both get the same current through them, and if those resistors both get the same voltage across themselves, then as far as the load is concerned, the circuit driving it could be either of those two circuits. It doesn't care. What it does is provide you an advanced circuit technique that, when used, can break down circuits very quickly in strategic times. Okay, so our goal will be really simple on the next page. We're going to find the current and the voltage through the load, RL. If they match, then we've proven that everything works. So let's take a look over here at what we have. Bear with me one second. Okay. Take a look at the circuit on the left. There's a 2 milliamp. I'm looking at the circuit on the bottom where it says analysis. Over here in the blue area here. Okay. I'm looking at this circuit. If 2 milliamps flows into a parallel circuit, each branch will receive 1 milliamp, correct? Each branch. Now, I didn't have to use Ohm's law, but I could have tried. I didn't use current divider, but I could have tried. But this circuit was easy enough. It's a learning model. I'm just trying to show you, without doing too many equations, that we can provide an analysis to this circuit. And we've determined that there is 1 milliamp rolling down the load resistor in green here. Okay? That's what we've determined. If you run the calculation for it, if you run the calculation for the voltage at the load, it's the current times the resistance at the load, which means 1 milliamp times 1,000. That leaves 1 volt. 1 volt for this resistor and 1 milliamp. That's what that load sees. It does not know there's a current source and a parallel resistor. It's giving you 1 volt and 1 milliamp. Now, if we go to the other circuit to the right, which looks completely different, heck, it's got a 2 volt battery driving it. It's got a 2 volt battery driving it because 2 milliamps times 1,000 is 2 volts. Where did we get that? Don't forget that we just did a source transformation here of 2 milliamps times 1,000 to give us the 2 volts of the battery. And the resistor, the 1K resistor, continues to live out here in series. Okay, so if we do a calculation here, we've got a 2 volt source. Let me change my marking size here. We've got a 2 volt source here, volt, and we've got 1,000 ohms out here and 1,000 ohms in the load position. Logic, you guys are pretty smart. It says, I have a 2 volt battery. How does the voltage break up between two series 1,000 ohm resistors? I hope you said 1 volt each, which coincidentally, according to the green that I'm covering here, that was exactly what we calculated as the voltage on the left circuit. So far the voltages have matched up, and of course 1 volt divided by 1,000 is 2 milliamps. you could have calculated this 2 milliamps. You could have just taken the current as the voltage divided by the total resistance, and you would have had 2 volts divided by 2K. Divided by 2K, 2 volts. That's 1 milliamp, isn't it? What the heck am I talking about here? It's not 2 milliamps. It's 1 volt divided by 1,000. My mistake. There it is. That's 1 milliamp of current. So as you can see, both circuits, according to the load, both circuits are driving the load with exactly the same voltage and exactly the same current. Now, maybe you were working the circuit on the right and you didn't like using a battery. You could have converted it to the circuit on the left, done whatever circuit technique you needed to get the current and the voltage of the resistor and be done with it. Very interesting, very interesting. So as we move through chapter 8 and 20 down the road, when the problems get nastier, meatier, uglier, bigger, harder, whatever you want to call it, when the circuits get that way, that's when a technique like a source conversion might work. Okay, so as our last slide, just to prove to you what this technique can do, I'm not going to solve this circuit completely through, but take a look at the mess up above. That's a 1 milliamp current source feeding a 1K resistor and a couple of 2K resistors on the right. Now, for whatever reason, we're calling those two 2K resistors the load. Okay, so the load could be 2 resistors, 3 resistors, could be 1 resistor. All I want is to know what the current through the 2K resistors is. That's all I want to know. I don't want to know anything else. Well, circuit 1's kind of nasty. It's a sort of series parallel. It's actually two parallel branches, but the branch on the right has more than one component, which kind of makes it a series parallel circuit. Okay, now look at the magic that happens with a source conversion. If I didn't mention it to you before, I'm going to mention it right now. Take a look at this, where the blue circle is. If you're going to do a current divider source conversion, you have to have a resistor in parallel with the source, the current source. It has to be in parallel. If you're going to do a voltage to current source conversion, the voltage and the series resistor have to be grabbed, whatever is there. So if you grab that resistor, the 1K and the 1 milliamp, you get circuit number 2 down here, and we do a source conversion to the battery, which is a 1 volt battery. 1 milliamp times 1,000 ohms is 1 volt. You draw the new circuit, and holy jackrabbits, what do you have? You have a chapter 5 series circuit. Which circuit would you rather solve? Remember, the only thing we want is to go get the current that's running through these 2 resistors. It would be very, very easy to just take the battery voltage and divide it by RT, which is 1 volt divided by 5K, and you get your current that's flowing through this circuit. And you get your answer. What is the current through the load? Isn't that special? Hopefully you found this very exciting, very interesting, and hopefully down the road you'll implement it when you're solving one of your circuits that you just don't like the way that it looks.